6.6 Trapezoids and Kites. Now, major thing to remember here, these are not parallelograms. That's the other side of our quadrilateral classification chart. These are quadrilaterals only. They are not parallelograms. The objective of this lesson is to verify and use the properties of trapezoids and kites. These are the last of our quadrilaterals. So kind of sad. I enjoy quadrilaterals. Hope you do too. So some vocabulary first here. A trapezoid is a quadrilateral, so 4 sides, with exactly one pair of parallel sides. So we have these parallel sides. We should probably do those in red. Parallel's always good in red, makes it stand out. Now remember, our parallelograms, both pairs of opposite sides were parallel. In a trapezoid, there is exactly one pair of parallel sides. These sides, the parallel sides, are called the bases. And we have 2 of them, base 1 and base 2. So we name this base 1 and base 2. The non-parallel sides are called legs. So here's a leg, here's a leg. Now it doesn't matter where your parallel sides are, they are always the bases. So if your trapezoid is facing the wrong direction, use those opposable thumbs and turn that paper so that your bases are on top and bottom so that it looks like your diagram. Don't let it hassle you. Oh, come back. The 2 angles that share a base are called base angles. There are 2 pairs of these. Your base angles are on top and on bottom. And then we have a very special trapezoid, an isosceles trapezoid. What do you suppose an isosceles trapezoid is? Yes, it is a trapezoid, so one pair of parallel sides, with legs that are congruent. So we have our parallel sides here, and then our legs are congruent, thus isosceles trapezoid. And isosceles trapezoids have some special properties. So let's go ahead and look at our first theorem here. If a quadrilateral is an isosceles trapezoid, then each pair, this is another one of those both things, each pair of base angles is congruent. So we have an isosceles trapezoid, one pair of parallel sides, our legs are congruent, then our base angles are going to be congruent. So here's a base, there's our base angles. Here's our other base, we'll label this base 1. Here's our other base, base 2, so our base angles are congruent. So we could name this one isosceles trapezoid, base angles congruent. Right? That's not too bad. So what does this let us do? Some algebra. We are told that CDEF is an isosceles trapezoid, and the measure of angle C is 65 degrees. We are to find the measure of angle D, E, and F. Well, the first one is really easy here. What's the measure of angle F going to be? Well, we know that base angles are congruent, so the measure of angle F is 65 degrees. All right, let's find the measure of angle D. How are we going to do that? Well, we have parallel lines. parallel lines cut by a transversal, we have same side interior angles. So if the C and D are going to be supplementary. So we can find the measure of angle D is 180 minus 65 is 115 degrees. And guess what? Our base angles here and here are congruent, so it's going to be 115 degrees as well. So that was pretty easy. And it looks like it's your turn. Go ahead and pause the video and give the next problem a try. That was a fun problem. We were given an isosceles trapezoid and asked to find the angle measures. And so first thing I did was identify my bases. They are the parallel lines. And then I know my base angles are congruent. So angle R is congruent to angle S, so their measures are equal. So the measure of angle S is 106 degrees. And then we know that using the same side interior angle theorem, that angle R and angle Q are supplementary. So I solve and I get the measure of angle Q is 74 degrees. And again, base angles are congruent. So angle Q is congruent to angle P, so their measures are equal. So the measure of angle P is also 74 degrees. So that's an easy problem. Part B says in problem 1, so back up here on our original isosceles trapezoid, it says if it were not an isosceles trapezoid, would angle C and angle D still be supplementary? Why, yes, they would. Our bases are still parallel, which means we have special angle pairs. These are still same side interior angles, and they are still supplementary. Okay, let's look at our next theorem. That was a good one. What's our next one? It says if a quadrilateral is an isosceles trapezoid, then your diagonals are congruent. So if we have an isosceles trapezoid, our diagonals are congruent. I imagine that will come in handy. To me, I look at it and I see congruent triangles because it gives us another side. Actually, I see side, side, side. I see a shared side there, and then these are congruent, so those triangles are congruent. Congruent triangles are always useful, and I bet it does some algebra for us as well. All right, let's go on to an example. Finding angle measures in isosceles trapezoids. We are given a paper fan, and the second ring of the paper fan consists of 20 congruent isosceles trapezoids. So we are looking at this isosceles trapezoid here, and there are 20 of them. And we want to know the measures of the base angles. Well, how are we going to start this problem? The best way to start this is to look at this triangle. And what kind of triangle do we have here? This is going to be an isosceles triangle, which is going to give us congruent base angles. So we can find this angle measure right here, angle 1. This is called the central angle, because we know an entire circle is 360. If we divide that by 20, we get 18 degrees. So if we know that's 18 degrees, then we can use the triangle angle sum theorem. Let's redraw. We're using these parts. Here is our trapezoid, our isosceles trapezoid, and we are using this triangle to get these base angles. And we know that it's an isosceles, so those are going to be congruent. We use the triangle angle sum theorem. So we found out this was 18 degrees up here, and that's going to tell us that these are both 81 degrees. And then we just use our same side interior angle theorem. These are supplementary, So we can find that these are 99 degrees because those angles are congruent as well. So some useful things with isosceles trapezoids. I think we'll skip the next problem. It's exactly what that one was, only with 15 angles. So we'll just skip that one. We'll go on to our next theorem here. And this is the trapezoid mid-segment theorem. Do you remember this? We've seen something very much like this before. What was it? It was our triangle mid-segment theorem. And what did we know about the mid-segments of a triangle? We knew that the mid-segment is parallel to the third side, and we also know that the length of the mid-segment equals 1/2 of the length of the third side. So let's look at our new theorem here. It says if a quadrilateral is a trapezoid, so we have a trapezoid, doesn't matter what kind of trapezoid, doesn't have to be special this time, this is all trapezoids. Our mid-segment is parallel to the bases, both of them. That should not be a surprise. And the length of the mid-segment is 1/2 of the sum of the lengths of the bases. Now that looks pretty familiar too, doesn't it? Well, take a look at our triangle mid-segment theorem back up here. And do you see the trapezoid in there? Okay, we are just looking at that line right there. And we can also look at this is what if our trapezoid, what if we extended the sides and turned it into a triangle? Our trapezoid mid-segment theorem adds the two bases. But let's consider our triangle. It says the length of the third side. What if we considered this top point another side, our other base? It just has a length of 0. So essentially we are adding our two bases. It's just one of them doesn't have a length, has a length of 0. So this is very similar. So our mid-segment is parallel to our bases, and we know that the length of the mid-segment is 1/2 of the sum of the two bases. Okay, notice how I put it in parentheses. That means it has to be done first. Very important. Or how else can we write this? Yes, one of my favorites. 2 times the length of the mid-segment equals the sum of the bases. Okay, again, has to be done first. I frequently enjoy multiplying by 2 more than I do by dividing by 2. All right, so let's see this theorem in action here. We are told that segment QR is the mid-segment of the trapezoid LMNP, and to find x. So we know that the length of the mid-segment is 1/2 of the sum of the bases, the quantity of the sum of the bases. So we simply substitute in, do our math, don't forget to distribute there, and we come up with x equals 3. But what if we decided to do it the other way? And we said 2 times the mid-segment equals the sum of the bases. Let's try that. Well, that would be 2 times x plus 2 equals 4x minus 10 plus 8. So again, we're going to distribute 2x plus 4 equals 4x minus 2. That equals a little more equal looking. Subtract 2x simply because I like my positive numbers. Like positive numbers equals 2x minus 2. Add 2 to both sides. 6 equals 2x. Guess what? We get x equals 3. So no surprise there. Doesn't matter which formula you use. Comes out the same. So now it's your turn. Go ahead and pause the video and do the next problems. You were told that segment MN is the mid-segment of our trapezoid, and to find the value of x and the length of MN. So use the mid-segment theorem. I did 2 times the mid-segment is the sum of the bases, and added it in, did my algebra, got x equals 6. If you did 1/2, you would get exactly, or 1/2 times the sum of the bases, you would get exactly the same thing. Doesn't matter how you do it. Just make sure you write your formula, substitute in, and do your algebra. And then to find the length of the midsegment, I simply substituted x back in. And we weren't asked to, but then I found the length of the other base, and we can look at it and see the top one is 10, the midsegment's 23, the bottom base is 36. 46 divided by 2 is 23, so it all looks good. And part B, how many midsegments can a triangle have? How many midsegments can a trapezoid have? It's 1. Only 1. There's only 1 midpoint on each of the sides. 1. It's not even a question. There's 1 midpoint of each segment. So, done and done. All right, that was trapezoids. Trapezoids are fun. Let's move on to our final quadrilateral here. Kites. And we're going to start this with some vocabulary. A kite is a quadrilateral, so that's 4 sides, with 2 pairs of consecutive sides that are congruent. Now, consecutive means next to each other, right? So 2 pairs of congruent consecutive sides. That means this side and this side are congruent, and this side and this side are congruent. This is different from our parallelograms. Okay, so good to go with kites. Now, the angles, sides, and diagonals of kites have properties. Imagine that. Let's look at our first theorem here. First theorem says if you have a kite, then its diagonals are perpendicular. So we draw in the diagonals, and we can mark that as a right angle automatically. Now, this is a theorem, so there's a proof to it. If you look at it, do you see it there? Do you see what we're going to use? Yeah? No? It's the perpendicular bisector theorem. Actually, it's the converse of the perpendicular bisector theorem. It says if the endpoints of our segment are equidistant from a point, then that point is on the perpendicular bisector. All right, so you can look that over. How are we going to use this? To find angle measures in kites. So if we are given that quadrilateral DEFG is a kite, find the measures of the missing angles. Well, if we know it's a kite, that first angle is super easy. So we know the measure of angle 1, that is a right angle, measures 90 degrees. The diagonals of a kite are perpendicular, and right angles, definition of right angle is 90 degrees. All right, so if we know that that measures 90 degrees, and all of these measure 90 degrees then, right? Because perpendicular is perpendicular all the way around. So if we know that measures 90 degrees, how are we going to find the measure of angle 2? Yep, you saw it. Triangle angle sum theorem. So we can get the measure of angle 2 is 38 degrees. And then, do you see the congruent triangles here? we have this and this, which means we have isosceles triangle, right? And then that's congruent in the middle. We have 90-degree angles there. Multiple ways of getting this. We could use hypotenuse leg or angle side. We have congruent triangles. So what is that going to do for us? That's going to make those two angles congruent there by CPCTC. So we used side, side, side postulate. It is a postulate. We should go back and fix that. Go back and change the theorem to postulate. And CPCTC, that these two angles are congruent. So if that angle measures 52, so does the measure of angle 3. All right, why don't you pause the video and do the last problem here with the kite. This was very much like the problem that we just did. We're told we have a kite. Find the measures of the angles. Angle 1 is 90 degrees because it's a kite and diagonals are perpendicular. And then we can find the measure of angle 3 by side, side, side postulate and CPCTC. But we can say now, and this is not an official theorem, that if you have a kite, the diagonals bisect the angles of the congruent sides, the included angle on the congruent sides. So that is these two angles up here and these two angles down here. So that's something that we can use. And then triangle angle sum theorem gets us the measure of angle 2. So we could say these angles are congruent as well because we have an isosceles triangle, right? These sides are congruent, these sides are congruent. So we would know both of those as well. All right, so those are fun. Remember your theorems that we have learned about these and all the rules, and you'll do fine. And now it is time to get out our classification chart and finish up our last two figures. All right, let's finish up our quadrilateral classification chart here. Let's start here in the middle. If you have 4 sides and 1 pair of parallel sides, you have a trapezoid. That's the definition of a trapezoid. And then if we add congruent legs, we have an isosceles trapezoid. So an isosceles trapezoid definition is trapezoid plus a pair of congruent legs. And then in addition, we know that the diagonals are congruent and the base angles are congruent on both bases. Now this is isosceles trapezoids only. All right, and for a kite, we have a quadrilateral with no parallel sides. Definition of a kite is 2 pairs of consecutive sides are congruent. Nobody's parallel, but we have 2 pairs of congruent consecutive sides. And for a kite, we know that diagonals are perpendicular. Now those are our official theorems. Our unofficial theorems here come from our side, side, side postulate, and our CPCTC is that the diagonals bisect the angle included between the congruent sides. So these here. And one thing we didn't talk about, but is really easy to see, is that the non-congruent side, so our non-congruent sides here, the included angle is congruent. And again, that is just side, side, side postulate and CPCTC. So our congruent sides, the included angles are bisected by the diagonal. Our non-congruent sides, the included angles are simply congruent. Up here with the diagonal and the congruent sides, they are not the same. This is not a rhombus. Okay, so the top angles here are not congruent to the bottom angles here, so be careful of that. All right, that is quadrilaterals. How much fun! Enjoy the homework and enjoy the quadrilaterals.